if at any point I say something that you don't understand, we're interactive. So you can wave your hand and wave at me, or just unmute and ask the question. Please feel free to do that. What I don't want you to do is I say something you don't understand and you don't take advantage of the fact that we're interactive and that you can ask me about that. So please just ask me if there's something you don't understand, okay? And if you want to make a comment or something, feel free to do that. But if there's so many comments that I feel I'm not making progress, then I'll ask people to save comments towards the end. But questions because you don't understand, those are definitely best if you don't save them, but just do them when they come up. So nod your head if you're willing to do that. And about half the people nodded their heads. And one of the people who didn't is smiling now because he knows he didn't nod his head. So I'm hoping that people will leap in if they have questions, if I say something they don't follow. Right, so are you ready to learn about the hilarious subject of computability theory? At least some people are. Okay, good. Some people are smiling. That's
we
good.
are. Yeah, let's go.
Okay, so I'm going to explain everything as I go along. I will explain what computability means, although most of you probably know that, and I'll explain which bits are hilarious. So, also I should explain, I've given this talk zillions of times before, but I haven't given it for about a year. So if I'm a bit slow or confused at some points, that's why. We can all be confused at the talk together. Right, so, I love this large pointer, by the way. It's great that you're all seeing a really big pointer, right? So
we are.
The trick of that is you go into the accessibility settings that lets you change the pointer size.
Mm-hmm.
And it's a wonderful thing for giving talks. I hate it when people point at stuff with their laser pointer and they know what they're pointing at, but I have no idea because it's a very, very, very tiny dot. So doing it this way is great. So let's learn about computability. So the first thing you need to understand is, what is a computer? So we think of computers as like this, right? Some machine that does stuff for us. And that's what computer means now. But before we had computers like this, computer was still a word, and it meant this, right? A person, a man or woman, it happened to normally be women, who executes an algorithm. Okay, so that's what a computer was, a person who executes an algorithm. So, right, algorithms have been around for a while, right? Euclid came up with a well-known algorithm in ancient Greece. Al-Khwarizmi came up with some algorithms, and then we named algorithms after him. But it's not until, so you guys are now seeing pictures of Alonzo Church, Kurt Gödel, and Alan Turing? Great. And these three people, all within a year of each other, published three different definitions, formal definitions of algorithm. So Alonzo Church came up with the Lambda Calculus. Kurt Gödel came up with recursive functions. The actual paper was published by Church's student, Stephen Kleene. And then Alan Turing came up with the one that we all know, Turing machines. So, you know, it's like buses. You wait 2,000 years for a formal definition of algorithm, and then three come along at once. Why did this happen? So let's go back to the turn of the century, not this one, the last one, 1900. And at that time, Göttingen was the place to go for mathematics. And David Hilbert became the leading proponent of formal logic, right? And he wanted what we all want, which is to put every mathematician out of business. So his idea, he referred to this thing which is called the Entscheidungsproblem, because it sounds much better in German. It just means decision problem. And the idea is you would write down a formula in formal logic, and then there would be an algorithm that would determine if it was true or false. So you wouldn't need mathematicians to prove things anymore. You would just write out the formal statement, and then your computer could determine whether it's true or false by applying the algorithm. And this is a great idea. Okay, so that was Göttingen, 1900. Now the scene switches to Vienna in 1930, where Hilbert, in fact, gave this impressive talk where he ended by saying, "We will know, we must know." And the very next day, Kurt Gödel gives this talk where he says, any sufficiently powerful formal system is undecidable. There will always be things that are either true or false, but you can't prove it's true. You can't prove it's false. And he showed this in a very clever way, right? What he showed is if your system's sufficiently powerful, like if it's arithmetic, say, you can actually encode any other formal system into that system. And in particular, you can encode the system into itself. So the system he had was arithmetic, but he wanted strings of symbols. Oh, wait, you can give each symbol a number. So now we've got a string of numbers, but you can encode that in a single number. What he did is he said, look at the prime factorization of a number. That's actually a sequence. The number of factors of 2, that's your first number. Number of factors of 3, that's your second number in the sequence. Number of factors of 5, that's the next one, so on. So you just look at the prime factorization, which is unique, and you can turn a single number into a sequence of numbers. So now we can take any sequence of symbols and turn it into a number. And we can formulate properties of numbers that correspond to other things. So in particular, we have x, b, y here is a formula over numbers x and y. But what it stands for is x is a proof of the formula y. And then we had this other thing, right? Bewegung x, x is a provable formula, which means there exists a y such that y is a proof of x. So now we have a property of numbers that's about numbers. So it turns out what you can do is you can make a statement number x is not provable, and you can make sure that the statement number x is not provable is in fact number x, right? That's quite tricky. I can't remember how to create that fixed point off the top of my head, but you can do it. So now you can make the statement, this statement is not provable. Ooh, right? As soon as you can do this, you are in trouble, right? Because there are only two possibilities. So the statement could be false, in which case it is provable, in which case, since it's provable and it's false, you've proved something that's false. So even in Germany in the 1930s, this was considered a bad idea. I'm not sure if some modern politicians would consider it a bad idea. And I'm making this facetious joke about Germany in the 1930s, but I'm actually reading a book right now. Where did it go? I can't show you the book I'm reading. I'm reading a book right now about the Vienna Circle. And it turns out that just like vaccines are being politicized these days, back then, even things like mathematical logic was being politicized. And the Nazis were really, actually the Nazis weren't so happy with this idea that you couldn't have a proof of a false thing. They did object to that, mainly because a lot of the people who were logicians were Jewish. Anyhow, politics aside, which is probably the best place to put politics, let's focus on the mathematics. If you could prove something that's false, that would kind of undo the whole purpose of proof. Okay. And basically that would mean you'd have an inconsistent system. So if we have what we want, which is a consistent system, it can't be that it's false, so it must be true. But if it's true, then it's not provable. So there's a true thing that's not provable. So that's not as bad as having a false thing that is provable, but it's still really annoying, especially if you're Hilbert. So this is the point, right? Hilbert said, we can know, we must know. And the next day, Gödel says, no, there are certain things you can never know. So at this point, the race was on, right? Because up to this point, people thought, right, all we need to do is look for it and we will find this algorithm that will be able to compute whether something is true or not. But as soon as Gödel comes up with this result, people begin to go, maybe there is no algorithm. Now, if you're trying to find an algorithm, all you need to do is write down the algorithm and people will look at it and say, yep, that's an algorithm. It will be just like Justice Stewart's definition of pornography. I know it when I see it. But if you want to show there is no algorithm, then you kind of need a formal definition of an algorithm. So the race was on. So the first person who came up with this was Alonzo Church, and he came up with the Lambda Calculus, which I guess many of you have been studying in your class. Is everybody familiar enough with what Lambda Calculus is? Anybody want to ask a question at this point? Okay, so he came up with Lambda Calculus, and of course, right, and then using that as his definition of algorithm, something is an algorithm if it can be written down in Lambda Calculus, he showed that there were problems that could not be solved by an algorithm. And in particular, right, he did the halting problem. He showed that you could not have a computer program that, given the number of another computer program, doing this encoding idea again, could determine if it halts or not.
Phil, I find that's pretty interesting bit of history there, because I always assumed that it was Turing who had first formalized the halting problem and proved.
Nope,
but Church did it first. That's
Church did the Lambda Calculus.
That is great. That's very interesting. I'll have to try and find the paper. 1936.
Yeah, and then just after that, there's another one saying, right, and that means you can't solve the Entscheidungs problem. So they quickly showed the existence of unsolvable problems. You could turn that into not being able to solve the Entscheidungs problem. And of course, right, Lambda Calculus is a very, very simple programming language, right? Here's the complete definition for untyped Lambda Calculus. So it's very, very simple. And right, I love that I get to work in a field of designing programming languages, but the main thing I used was designed in 1932, when the only computers around were people executing algorithms, not the stored program computers that we have today. And of course, right, now, right, I do functional programming. Industries pretty much conspired to ignore functional programming. So everything I and my colleagues have done for years and years and years. And then all of a sudden, Lambda becomes very popular, right? And Python gets Lambda, C++ gets Lambda, Java gets Lambda. So here's Duke, the mascot for Java, looking very smug because they've got Lambdas in Java now. Well, congratulations, Duke. You're finally caught up with where Church was back in the 1930s. So Kurt Gödel now enters the story again. So Church was on the faculty at Princeton, and Gödel came to visit Princeton, something to do with all that stuff going on in Germany that he needed to get away from. And he looked at what Church had done with Lambda Calculus and reacted the same way that most industrialists react now when you show them Lambda Calculus, and they say, that must be wrong. I don't understand that. What's going on there? And to be fair, right, Church did not necessarily do a great job of explaining why it should be the case that anything that an algorithm does could be done by Lambda Calculus, right? That was far from obvious. He just sort of posited it, Church's thesis. So Gödel said, no, that must be wrong. And Church said, fine, you think this is wrong, tell us what you think is right. And so Gödel gave a sequence of lectures on general recursive functions. And he said, this should be the definition of algorithm. And Stephen Kleene, who was Church's student, took notes on these lectures and then published it with attribution to Gödel. So this is the second definition, recursive functions. And you can see, right, that's sort of the way we do it, right? You define this function over 0 in terms of something, and then this function for y plus 1 in terms of the same function applied to y. That's our normal definition of recursion. And so he said, this is what it should be. And then Kleene and Church sat down and did the proofs, and they showed that anything that you could write with recursive functions, you could write in Lambda Calculus, and anything you could write in Lambda Calculus, you could write with recursive functions. So they were equally expressive. They went back to Gödel and said, look, you didn't like our definition, but it's the same as your definition. And Gödel said, oh, my definition is the same as yours. I really don't like yours. Mine must be wrong. So it's a complete impasse. The tension builds. And onto this scene comes Alan Turing, who at the time was an undergraduate student at Cambridge. And with Max Newman, he'd come up with his own answer to the question of what is an algorithm. And he did it in this very mechanical way using Turing machines. But he did something really important. He actually gave an argument to say, why should what this machine can do be the same as what a computer, that is a person following an algorithm, can do? And he justified everything, right? So he said, right, so we're going to write things down. When you write things down, you can only write a finite number of symbols. There can't be an infinite number of symbols written in one square because there's not room. Right? It would eventually get too small, you couldn't tell them apart. So it must be a finite number of symbols, and you must be able to look at only a finite number of symbols at one time. And his proof for this is wonderful. He explains, this is because if you look at the number 99999999999 and the number 99999999999, so one of those was 15 nines in a row and the other was 14 nines in a row. He says you cannot distinguish them at first glance. So that was his evidence that you could only look at a certain finite number of symbols at a certain time. So in this way, he showed that what the Turing machine could do is what a computer could do. So this was essentially philosophy, but it was very important philosophy. And right, so Turing came up with this completely independently. Church and Gödel had published the year before. He didn't know about it. When they discovered this in the library, the magazines finally, the journals finally arrive, and they go, "Oh, we've been scooped. How annoying." But Newman wrote to Church and said, "Here's this other rather different style of proof done by this young student." And they all agreed that it was different enough that it was worth publishing. Of course, you can see why. Because when Gödel read what Turing did, he was finally convinced by the argument. At this point, they'd proved that what Turing machines could do is the same as what recursive functions could do, is the same as what lambda terms can do. And so this finally convinced Gödel that the three of them were in fact right, whereas before Gödel had thought that his own idea was wrong. So one thing philosophers like to argue about is mathematics invented or discovered? So I want to argue that if you have three people independently come up with three quite different ideas that turn out to all capture the same concept, that's not just something in our heads. The reason that all three of them are finding the same thing is because there's something out there that they have found.
Okay, I have a question for you, Phil.
Yeah.
This is something that I've seen a number of times, that you know, that essentially you're a Platonist. You believe that it's discovered that these things exist out there, and yet I somehow find it contradictory, maybe, with the fact that so much of your career is built on the logics that were developed by Brouwer and Kolmogorov, who were not Platonists, as far as I know. I mean, Brouwer certainly not. I think Kolmogorov was also, you know, a strong constructivist. So how do you kind of like fit that together? I mean, isn't kind of the hallmark of Platonism that
Their
if it's
math, I have to like their philosophy?
no, but I mean, if it's out there, then excluded middle is true. And yet, right, if it's already out there to be
Oh, no,
discovered.
I think that both classical and intuitionist logics are out there. I wouldn't say one has priority over the other. So in that, I certainly do disagree with Brouwer, who would say constructivist is more correct. I just think constructivist is more useful for certain purposes.
Mhm. But doesn't the the Platonist view, though, presuppose that excluded middle is true? And isn't that an objection that you would have to constructive logics, or not?
How did I end up presupposing excluded middle? I didn't know
Well,
before.
I think when you think that it's discovered, then that means these mathematical objects exist out there already, preformed. And so
That's
then,
excluded middle?
but that leads to excluded middle, because then it's either true out there in this Platonic universe, or it's not true out
Well,
there.
certainly when I was talking about Gödel's proof, right, I did use excluded middle,
Mm-hmm,
right? I said this formula is true or false.
mm-hmm.
So maybe a way out of it is if you're a strict constructivist, then Gödel's construct doesn't work. But I don't think that's true. That would be neat if it worked.
I don't think it's true either. I think it still works. Yeah.
Let's
You
move on.
still
That's a debate that has been going on
absolutely.
for literally 2,000 years. So you and
I
I will
know.
not
I
resolve
know.
it.
It's just actually, though, it is something that I've always been curious about your opinion on that point.
Well, the one thing that I will mention, right, is you said these guys believe this. Isn't that a powerful argument? I have to point out to you that I really love all the logic done by Gerhard Gentzen, who we'll get to in a bit.
Of course. Yeah.
He was Nazi.
Yeah.
I do not agree with everything that Gentzen thought. I love his logic. There are other things he thought that I very much disagree with.
Okay, let's go on.
Right, so Gödel was 28 when he undermined the life work of Hilbert, who at the time was 68. Turing was 23 when he resolved this dispute between Church, who was 33, and Gödel, who by then was an untrustworthy 30. So many of you in the audience here are young. You know what to do, right? It's your job to keep explaining to your elders, people like me, when we've got it wrong. And that finishes part one. So now I'm going to go on and talk about the advertised subject, propositions as types. But before I do that, this would be a good place to pause. Are there any other questions for people who want to fight philosophy?
I don't want to fight philosophy. I've got a question with regards to, so where kind of Gödel kind of blatantly came out and said, okay, Lambda Calculus must be wrong. How did he justify that? Because it sounds like Church and his colleagues took a very mature, non-defensive approach and said, okay, and they went to his lectures and they listened and, and they obviously proved that they were both similar. But I can imagine in some circumstances when you have competing theories, for someone to say something is wrong, how did he justify it? Did he come and say, I think it's wrong because of A, B, C, or D? Or was it much more like a gut kind of feeling to say, I think you're wrong, without kind of proving it? Do you have any kind of insight to that at all?
Well, this is the point, right? Which was, as I mentioned, right? Church just said, here, this is it. Anything a computer can do, this can do, but without giving a reason. So the Church had not provided any reason for believing this. And then Gödel decided that his reasons for why this must be enough were perhaps inadequate. So Gödel started mistrusting his own intuitions. It was only when Turing came in with actual reasons for these things that Gödel was finally convinced. But that's a good question. I don't actually know enough of the details about why Gödel was unconvinced. It'd be interesting to go back and study that in more detail. I've not done that. Very good question. Any other questions?
I have a question. I guess hopefully you can hear me. I was just wondering, because you were talking about a statement not being provable. So I was just wondering if a statement that isn't provable, can it still be used in mathematics, or is it just something that gets discarded?
Oh, so there's this whole subject of proof theory, and a lot of logic is about, well, what are we going to consider as a proof? Does that answer your question?
Yeah, kind of. Thank you.
And in fact, I'm about to say a little bit about what constitutes a proof and what proofs look like for one model of proof. But any logician, so there's a large branch of logic, the branch that I'm interested in, which is called proof theory. And the first thing you talk about is, what are we going to consider to be a decent proof? So that's sort of the first question that you answer. I'm going to give you an answer to that, but there are many, many, many answers out there. Okay?
Thank you.
And also sometimes things that are not proven are heavily used, like the Riemann hypothesis. It's referenced in thousands of papers and it is not proven.
Oh, wow. Okay. That's really interesting.
Well, you can also have things like the axiom of choice. And it turns out there are models of set theory where it's true and other models where it's false. So you can't really say whether it's true or false, but many proofs make use of the axiom of choice. They'll just say, we'll assume this is true.
complexity theory proofs often have a huge number of of assumptions, like in structural complexity theory. If P is not equal to NP, then you can prove these towers of interrelated complexity classes. So yeah, so oftentimes people will use an assumption that's unknown whether it's true or false, and carry forward from there. I mean, well, recursion theory is a lot like that as well, right? Say, well, what if we had an oracle to solve the halting problem? What would be true then?
Yeah. So I guess if a proof has a lot of assumptions, can it still be like a valid proof? I guess
Sure.
Is there like a cap of the amount of
So
assumptions?
one of the things we're going to see in just a moment, that the way that a proof looks is it has some assumptions at the beginning. And we're going to be interested in proofs where you discharge all those assumptions, but you could also have proofs where you don't discharge all the assumptions. And that would still be a valid proof. You would just have an assumption. Okay, so I mentioned Gerhard Gentzen. Here he is. And right, so I was talking about what young people could be up to, right? So as an undergraduate, you might do something like define Turing machines. Are any of you undergraduates? Okay, great. Okay, so you can go off and define Turing machines. Are any of you graduate students? Okay, some of you are graduate students. So you might think it's too late for you, but let me tell you what you can still do when you're a graduate student. So Gerhard Gentzen, for his, what was essentially his doctoral thesis, came up with natural deduction, which is the main form of logic that we use today, the most common form of logic, the most famous one. He also came up with sequent calculus, which is the second most widely used formulation of logic. At the time, backwards E was already used for meaning there exists. And the notion of for all had been around since Frege and Peirce in the late 1800s. But Gentzen, in his 1935 PhD thesis, said, oh, well, by analogy with backwards E, let's use upside down A. So the symbol for universal quantification is also due to Gentzen. So two main forms of logic that we use today, and one of the most important symbols in logic, all due to Gentzen. So for those of you who are PhD students, it's not too late. You can do something, you should do something of similar magnitude. And in fact, I'm going to focus on this, but this formulation of logic is exactly the one we use today. And here's some of the same rules as here. So this is, we've got the rules for implication. So this says, if assuming A, you can prove B, then you know A implies B. And this says, if you know A and you know A implies B, then you know B. And that's exactly what we've written here. And if you look, you see I'm using exactly the same notation. The only difference is his letters are in German and mine are in English. But otherwise, it's exactly the same rules. And then there's some more rules here that we'll focus on. The ones for conjunction. So this says if you have a proof of A and a proof of B, you may conclude A and B. And then this rule says if you've got a proof of A and B, from that you could conclude A. If you have a proof of A and B, from that you could also conclude B. So the key insight that he had, and this was true for both of the systems he described, is that the rules come in pairs. Sorry, I'm going to just, give me just 1 second. I'm getting dry. I'm going to have a sip of water. The key insight he had is that the rules come in pairs. And so we've got these introduction rules, and they're called introduction rules because the connective, either implication or conjunction, appears beneath this line, right? So the things here above are your proof, and then the thing below is what you've proved. So here it says, well, if you can prove A and you can prove B, you can conclude A and B. Here it says, assume A. So this is one of our assumptions. And if from that you can prove B, you can conclude A implies B. And notice that we've then written a little X next to this and an X next to this. And that's to say, this assumption has now been discharged. So up to this point in the proof, A is just an assumption. We've just assumed it's true. At this point, we're no longer assuming A is true. We know A implies B with no assumptions. And then how do we use, and the idea is this is how you create something, and then this is how you use it. So if we've proved A imply B, what do we know? How can we use it? Well, we use it with this rule, which says, well, if you know A implies B, if you have a proof of that, and we have a proof of A, then you may conclude B. And most of you will have seen that rule before. It goes back to the ancient Greeks, but the name just goes back to the Middle Ages, to the 1300s or so, where they called it modus ponens. And then here again, right? So if I've proved A and I've proved B, then I know A and B. What can I do with that? Well, I originally had proofs of A and B, right? So if I know A and B is true, I can extract from it A, or I can extract from it B. Okay. So that's sort of the most technical stuff I'm going to do. Are there any questions about that? Have you guys seen those connectives and those proof rules before? Okay, right. Lots of you have seen them before. Anybody have any questions about them? Okay, so let's do an example. So here's an example of a proof. Let's prove that B and A implies A and B. Well, that's really kind of obvious, isn't it? Do I really need to prove that? No, it's blindingly obvious just from the meaning of and. But, right, we're checking out our proof rules. If I couldn't use the proof rules to prove it, then the proof rules would not be complete because it's obviously true. So I better be able to prove it. So can we prove this? Okay, so remember what we do is to prove blah implies blah, you assume the first blah, and then from that assumption, you conclude the second blah. And notice that the assumption in this case can be used any number of times. So here we've used it twice. And now I've assumed B and A, but from that I can guess, right? I know A must hold. And from B and A, I also know B must hold. Wait, I've got a proof of A, I've got a proof of B, so I've got a proof of A and B. So now I can discharge my assumption, and I know B and A implies A and B. I've discharged both these assumptions. So with no assumptions, I know B and A implies A and B. Everybody convinced? And any questions about that?
What does it mean to discharge an assumption?
Oh, it means, so if I have a proof of some assumptions, it means if these assumptions are true, then the conclusion is true. Right? So if I have a proof that uses the axiom of choice, say, it says, if the axiom of choice is true, then you know this conclusion is true. But if you've discharged an assumption, it's not an assumption anymore. If I've so at this point, before I discharge the assumption, I know that if B and A is true, I can conclude A and B. But when it's discharged, now I've got this formula. I say, without any assumptions, I know B and A implies A and B.
I understand now. Thank you.
Good question. Thanks. Now, the key thing is you can simplify proofs. This is why it was so important, right? They've been doing formal logic since the late 1800s, right? Really the mid 1800s with George Boole. And Hilbert in particular came up with a very famous formulation of logic, but it didn't have this important property that Gensen's had, which is that the rules come in pairs. And this idea of the rules coming in pairs was very important because it meant you could simplify things. So what Gensen claimed is if you ever had a formula that appeared somewhere in the middle of a proof, that you could get rid of it. The only formulas that you needed in a proof are the conclusion and the assumptions and any parts of those, but nothing else. So here we've got a bigger proof, right? It's got A implies B, right? Which is not the conclusion, and we haven't shown any assumptions here, but it's not necessarily one of the assumptions. So he says, nope, this happens, you can get rid of it. There's a formula in the middle of a proof, you can get rid of it. And the reason why you can get rid of it is you must introduce it and then eliminate it. And you can always simplify those away. And by the way, right, the fact that you can do the simplification sort of justifies that the rules fit together, right? Why from A implies B and A am I allowed to conclude B? Well, think about it, right? A implies B means if you assume A, you can prove B. Oh, look, here's A proof of A. So we just copy that everywhere the assumption is used. We're no longer assuming A, we've got a proof of A, and that gives us a proof of B, right, with no assumptions. And if this works, yep, you can actually see this, an animation of the simplification. Just run that one more time since the arrows land on top and you can barely see it. Okay, so that we can simplify those proofs, and
That's
even
very
more
nice.
easily.
That little animation, very nice.
Right? If right, so we've got a proof of A and a proof of B, and that gives us A and B, but then elimination gives us A. Oh wait, right? We've got a much more direct proof of A. It's right here. So we can just copy that down. Right? So we can always simplify to get rid of these intermediate formulas. And Gensen used that in a very important way. He said, okay, you can always get rid of any formulas other than those in the assumptions and conclusions. And then he used this to show that the logic is consistent, that you cannot prove false. Why? Well, say you had a proof of false, then your conclusion would be false, there'd be no assumptions, and you'd have to write out the proof using only false and its parts. It has no parts, right? It's just false. And the assumptions and their parts, but there are no assumptions. So you'd have to write out a proof of false using nothing but false. You can quickly look at the proof rules and go, nope, nothing's going to work. So he could show that there was no proof of false and show the consistency of the logic. So this idea that you could get rid of these intermediate formulas, which went by the name cut elimination. So I mentioned he came up with this other thing, sequent calculus. He actually, right, so he's proving, right, that there are no roundabout proofs. He called it, that was the way he said, there are no roundabout proofs, meaning you don't need any concepts that don't appear in the assumption or the conclusion. So if you don't have an imply sign in the assumption or the conclusion, you don't need an imply sign anywhere in the middle of the proof. So he's showing there's no roundabout proofs. Oddly, to prove that, he had to do a roundabout proof. He came up with a different system, sequent calculus, showed that had the property. It was called cut elimination there. And then said, so therefore the same property must hold for the natural deduction, which is equivalent to sequent calculus. Only about 30 years later, Pravets came up with a direct proof. which is the one that I've showed you.
Philip, can you just briefly on that? I mean, you sort of previously said that you know, natural deduction is really where it's at, and sequence. But I kind of grew up using sequence through New Pearl, and I don't know. I find the sequent calculus actually easier, especially for classical proofs, easier to teach for classical theorems that are not constructive. The sequent calculus is just, you know, a kind of a boring algorithm to do the proof search, whereas in the natural deduction proof, I mean, you can make an algorithm to do it and then maybe simplify the proof, but oftentimes natural deduction proofs require some cleverness when you are dealing with, you know, using the rules that added make it classical. If you have to use, if you're in that space where you're trying to prove a theorem that's classically true, but not intuitionistically true. Thoughts
All I
on?
said about natural deduction is that it's the most widely used. Sequent calculus is second most widely used. That's just a popularity contest. If you prefer sequent calculus, I'm not going to argue with you.
I don't want to argue. I'm just wondering about your thoughts on that.
The reason that I did this using natural deduction rather than using sequent calculus is in sequent calculus, every time you write down a formula, you have to write all its assumptions with it. So that's wonderfully clear, but uses up a lot of space on the page. And this, you have less repetition. I think that makes it easier to write down and easier to look at. So that's an advantage of natural deduction. And the other advantage, of course, is it's going to correspond very well to something that we'll see in a minute. Okay. Right, so these are just what I showed you without the animation. So let's look at let's look at an example proof and see how it simplifies. So here I've got some proof of B and some proof of A. I'm not going to tell you what they are. And from that, I get a proof of B and A. And then we've got the proof we had before, right? That B and A implies A and B. And then here's our conclusion, A and B. So from what was just said, right? Just using these assumptions, I should be able to prove A and B directly. Because all these other things, right, don't satisfy the subformula property. They're roundabout. So can I do that? Well, let's use the simplification rules that I just showed you, right? So we should say, right, this assumption is used twice. Let's replace it with this proof of B and proof of A, and therefore proof of B and A. So, right, we've copied this over now. So now there's no assumption, and we just prove A and B. But we've got from B and A a proof of B and A, and then a proof of A, and the same thing here. We can simplify those. Oops. Oh, I have to go to the next slide, sorry. Right, and now we've got our direct proof, right, which is from the proof of A and the proof of B. We can, of course, conclude A and B. Okay, so do people follow how that proof simplified? Okay, and then here's the simplification written out on one slide. Okay, that's all I'm going to say about Gensen for a minute. Any questions about Gensen? Okay, so now we're going to go back to Alonzo Church. So I mentioned Church's Lambda Calculus. So interestingly, when Church started, he's a logician. He was interested in logic. He wasn't interested in computation. He came up with what a computer scientist would call a macro language for expanding out formulas in logic. And that was Lambda Calculus. It was supposed to be a way of writing formulas down more compactly, basically. And the paper where he writes it, he says in the introduction, that it is quite general, and indeed it may have applications besides its use as a logic. So, and then later was the idea that, oh, this could do everything the computer can do. But it turned out, right, what I've shown you up to now is untyped lambda calculus. Turns out that that lets you write down the equivalent of infinite formulas, right? You've got a little computer program that expands out to an infinite formula. And it turns out if you're allowed to write down infinite formulas, you can prove false. So in fact, it turned out that his logic was inconsistent. So it was just as well that you could use the lambda calculus for other things having nothing to do with logic. However, Church also came up with this scheme that rendered it useful in logic because it became consistent. It could no longer do all recursive functions, right? So it's not as powerful as anything a computer can do. But now, in fact, every program you can write down terminates. And so you can't get programs that generate infinite formulas. So the paradoxes go away. So this was called the simply typed lambda calculus. And it was important because you could then use the lambda calculus within a logic without introducing inconsistencies. So it looked like this. It said, okay, the formula lambda xn, right? So this is, right, so here x is a variable and n is just going to be some terms. This might be, if n was the term x times x, this would be lambda x, x times x, the squaring function. So it says, okay, let x, so in that case, a and b would both be a natural number. So, but in general, let x have type A. And if x has type A, you can show that n has type B. Then what's lambda xn? It's a function that given an A returns a B. What about function application? Well, if L is a function from A to B and M has type A, then L applied to M has type B. In fact, that's all there is in the very simply typed lambda calculus. But what I'll do is I'll show you one that also has pairs in it. So if M has type A and N has type B, then MN is an AB pair. And then if L is an AB pair, the first projection of L would have type A, and the second projection of L would have type B. So let me show you a simple example of such a program. Right? It's the program that takes a BA pair and returns an AB pair. So what's it going to do? It's lambda Z, so Z is a BA pair. And then we take out the second projection of that, that would be an A. And we pair that with the first projection, that would be of type B. So the final result has type A and B. We can just do the type checking, right? If Z is a BA pair, then pi 2 of Z would be an A. If Z is a BA pair, pi 1 of Z would be a B. And then pi 2 of Z paired with pi 1 of Z would be, whoops, oh dear, would be an A paired with a B. Okay? Okay, so this program just takes a pair and swaps the two components, right? So now we can look at how do you evaluate a program. So you guys probably all know, right, the beta rule for lambda calculus. So if I have lambda Zn applied to M, that's going to reduce to what? Somebody can leap in there with the answer. Right, so if this was lambda x, x times x, applied to 3, what's it going to reduce to?
3 times
3 times 3, right? So you take your argument, your actual argument, and you substitute it for the formal argument z. So what does that, oh, and when we do that, it's going to be well typed, right? Let's see why. Just go back and do that again. Right, so we're going to take Z of type A and replace it with this term M of type A. So before we did the typing assuming Z has type A, but now M also has type A. And so we know N has type B. So the result, just like lambda Z N applied to M has type B, N with Z replaced by M will also have type B. And that's exactly what this animation is showing us. Okay? Right, and even easier, right? If we've got M of type A and N of type B, gives us an MN pair, and then we take pi1 of that, that would have type A. So that's going to reduce to M, but M has type A. So again, as we do the reduction, the type doesn't change. Again, we can animate that. Okay, any questions about that? And there's the same thing just written out on one slide without the animation. And you can actually use this to prove that any simply typed program terminates. And in fact, Turing wrote out the first proof of this. But the basic argument is you saw that we had this intermediate type, right? Either A implies B or A times B. And when you reduce, you get rid of those intermediate types. So the set of all types in the program is getting smaller in some sense. You have to use a multiset because you are doing duplication when you substitute. But you can show that ultimately things just keep getting smaller and smaller, and you can't do that forever, so it must terminate. Okay, so let's look at evaluating a program. So here's an NM pair. So like B might be int and N might be 3. And A might be int and N might be 2. So this is the pair 3, 2, which is a B followed by A pair. Oh, and here's this function we wrote before to swap things, right? It takes a BA pair and returns an AB pair. So we're going to apply this function to that pair. And let's evaluate that, right? So we'll do beta reduction. We'll copy this NM pair in place of that variable Z. Just copy it over. Right, there we go. So we've copied it over. And now we've got pi2 of NM paired with pi1 of NM. And again, right, pi2 of NM just simplifies to this M, and pi1 will simplify to M. Oops, oh right, that's the next one. Just run that again in case that was too quick. And indeed, so that says that our initial program, right, this whole thing, what does it simplify down to? The final AB pair we get out is just M paired with N. Okay? And here's the evaluation written out on one slide. Okay, so at this point, James, I hope you had time to do this. I know I got this to you rather late, but did you manage to send everybody the rose-colored glasses?
No, I apologize.
That's my fault. I got them to you too late.
All right.
So I want you to just pretend that you've received these rose-colored glasses. So I want you to do the unboxing now and pretend you're putting on your rose-colored glasses. And if you put them on, you will see something amazing, which is, right, if you put on rose-colored glasses, you won't be able to see red. So all the red bits will go away, and you'll just be left with the bits in blue. And at that point, you will realize that all of this stuff with simply typed lambda calculus we've seen before, right? It was just Genson's logic. So these two things are in a very close correspondence. And right, what's going on here? So when we said, let's go back to this one, right? When we said here, okay, I've got a proof of B and a proof of A, and from this I've got this complicated proof of A and B. So this formula here is a proposition. This is a proof of that proposition. And the proof, as we saw, simplifies. Now, that proposition becomes the type of this term. So, and the proof of the proposition becomes the typing derivation for that term, the evidence that the term has a type. So a term having a given type corresponds to a proof of the corresponding proposition. And furthermore, we can see that whereas before we were simplifying a proof, now we are evaluating a program. So we've got three different things going on here, right? The propositions correspond to types. The proofs of the propositions correspond to the typing derivation of the term, which is in one-to-one correspondence with the term. So the terms encode proofs. And here where we were simplifying the term, we were evaluating the term that corresponds to simplifying the proof. So it's three levels: propositions as types, proofs as terms, and simplification of proofs as evaluation of terms. So that's sometimes called propositions as types. It's sometimes called the Curry-Howard isomorphism. And here's a drawing by Luca Cardelli of what he called the Curry-Howard homeomorphism, right? Because here's how we write the constructors in logic, but here's how we usually write them as types in a programming language. So, and some people point out, you mentioned before Breuer and Kolmogorov and hiding. So if you look back at constructive logic, all the same ideas are there. So some people say you should call this the Breuer, Hiding, Kolmogorov, or BHK correspondence. So there are many, many different names for this concept. Curry, by the way, did this for a different version of logic involving combinators, and then William Howard was actually the first one to write it out for Lambda Calculus. But more importantly, he then said, well, wait a minute, that's the simple types. What happens with something like for all? And so he invented what are now called dependent types as a way of having a type theory that corresponded to what's going on with quantifiers in logic. And that was extremely influential. That led to work such as Automath by De Bruyn and Martin-Löf's type theory. And from there, let's see, have I got everything? Yeah, so here's Howard's paper about it, which was in a Festschrift to Curry. Right, so this is what I explained to you, right? We've got propositions as types, proofs as programs, and normalization of proofs as evaluation of programs. Now, the interesting thing about this, when I first saw this, I just thought, oh, that's a clever trick. It's not really very significant, is it? And I didn't realize that it would end up being the basis for my entire research career. And one of the reasons why is, right, what I've just showed you is this bit of the correspondence. But it turns out that pretty much every interesting concept in computing has a corresponding interesting concept in logic. So the first time I understood this was going on was with this proof that continuation passing style in programming languages corresponds to classical logic. It turns out what I've been showing you is for intuitionistic logic. And when people, this idea was extended to classical logic after I had first seen it. So I think I was first shown it in 1983. And I think the extensions to classical logic came about 88 or so. So a little bit later. And when somebody showed me that was when I began to have an inkling that there's something interesting going on here. And then much later, I did work with monads, and then somebody showed that monads actually corresponded to modal logic. So almost every interesting idea you can name has a correspondence. And what turned out to be extremely productive is that Girard, so Girard comes a couple of times. So how many of you have used functional programming languages like Haskell or OCaml?
I hope.
So
I
those
hope
languages
everyone here.
those languages have type systems based on what's called the Hindley-Milner scheme, which lets you do type inference in a neat way. And in fact, again, that was discovered twice, once by the logician Roger Hindley and once by the computer scientist Robin Milner. And then there's a nice generalization of that, which is the logic of basically second order logic, where you can quantify over propositions, which Girard came up with and called System F, or polymorphic lambda calculus, which is just the basic generic type system that underlies all languages with type variables, which John Reynolds came up with just within a couple of years of each other. And then much later, the same Jean-Yves Girard came up with a new form of logic called linear logic, which was basically about, remember, sorry, I have to skip back a bit. Right, but here, when we had this proof, the point was we have this assumption, B and A, but we use it twice, right? So when we copied this, it got copied twice. We now have two copies of these things. So you might want to say, well, what about the ones where you don't copy? What about the ones where you don't throw away, where you use everything exactly once? And that's what linear logic is. And that turned out to be very useful in computing. And one particular use of that is something that Kohei Honda came up with called session types. In fact, he was directly inspired by linear logic. Session types have 4 connectives in it: input, output. So ordinary logic, right, you've got or and and. Those are the 2 main connectives. And they're dual to each other. In linear logic, you've got 2 dual pairs. You've got 2 kinds of or and 2 kinds of and. When Honda did session types, he had input, output, and one of the kinds of ors and ands from linear logic. So it was part taken direct from linear logic, and then part, well, you've got communication channels, obviously you have input and output on them. Much, much later, so Kohei came up with that in 1993. Much later, in 2010, Frank Fenig and Louis Carras went, well, actually, input is exactly like the other connective of linear logic. Output is like the other connective pair. So you had 4 main things in linear logic, and they turned out to be the 4 main things in session types, but it took nearly 20 years to see it. And so, right, every functional language in the world is based on lambda calculus, and pretty much every proof assistant is based on this propositions as types correspondence and using terms in lambda calculus to encode proofs. one way or another. Okay, so that's the end of the second part. Are there any questions about that?
Maybe, oops, maybe this is a question for the end, but I'm sort of interested if you went back up to, you know, the linear logic session types correspondence. What about, do you think there's going to be any useful propositions as types work that you can do with Plutus as you've designed it to, for example, come up with a specification logics or smart contracts where the proofs that the specification is inhabited are essentially the programs? Have you considered that at all?
I have considered it.
Mm-hmm.
I do not know how to do that. I would love to know how to do that. It should be possible to do that. I do not know how to do that. That is a really, really good question.
Well, it's something that I would personally like to, you know, participate in and maybe inspire one of my students to follow. But, you know, we, you
Please
know,
do.
yeah,
That would be an amazing thing to do.
yeah.
In fact, right, the next part is about Plutus. Does everybody, I guess not everybody here knows about this. Or does everybody know about it?
Oh,
Tell me what they know, James.
oh, almost everyone knows about the IOHK lab, I think, you know, about Wabble and that we're working with IOHK and Cardano.
Right, okay. So
it wouldn't hurt though for you to spend a few minutes describing it.
right, so let's see. So cryptocurrencies are very much in the news these days. There's a firm called IOHK, which has a cryptocurrency called Cardano. And quite unusually, they're really interested in having a sound academic basis for everything they do. So a colleague of mine at Edinburgh, Aggelos Kiaios, is their chief scientist. They use proof of stake rather than proof of work, which is very important because, you know, cryptocurrencies based on proof of work literally use as much energy as the entire country of Argentina. Proof of stake uses much, much less energy. It solves the consensus problem in a different way. And he came up with the proof of stake algorithm used in Cardano, and then they proved all the properties that you want of this kind of algorithm. And then, so on top of the basic cryptocurrency, you then want a smart contract system, something where you can have a computer program that decides whether you're allowed to transfer the coin and the currency from one holder of the coin to another holder. So that's what a smart contract system is. And so that's, so I was hired to consult on this. Rebecca, who since left the team, was doing the main design work. And then I did the really important thing, which is I convinced them to hire Manuel Chakravarti to lead the team. He's another person from the Haskell community. And then we managed to hire Michael Peyton-Jones, who happens to be Simon Jones, if you know who, Simon Peyton-Jones, if you know who he is, his son. And like his father, he's very clever. In fact, everybody on the team is very clever. I won't go through them all in detail. So we've got the Plutus, which is basically a library for Haskell. Now, if you know Haskell, you know it's quite a complicated language. And even though a bunch of languages are supposed to be great for doing mathematical reasoning, Haskell has kind of grown really, really complicated. So it would be it's, you know, a very large compiler. and being sure that everything worked properly and that your programs meant what you thought for this really rather large language could be difficult. But that's okay. One of the nice things about functional languages is you can take a big, complicated language and simplify it down to a tiny core language. So in fact, that's the way the Haskell compiler works. There's a much smaller language called Haskell Core that everything compiles into. Haskell Core is not far off of what I mentioned before, right, which was System F. So remember, right, we've got this correspondence that Church came up with Lambda Calculus and Gensen came up with natural deduction. And then we've got Jean-Yves Girard comes up with System F, and John Reynolds comes up with polymorphic Lambda Calculus, both at the same time. And in fact, Haskell Core is quite similar. It is basically an enlarged version of System F. So it turns out we don't need all of Haskell Core. What we do is we just say, right, we'll use the Haskell compiler, compile into Haskell Core, and then we'll translate that into System F. And System F, which we call Plutus Core, is what actually runs on the blockchain. So that's a very, very simple language, right? One of the things that you want on a blockchain is, right, once you put your smart contract on the blockchain, it stays there for as long as the blockchain is there, which one hopes would be a very long time. In the existing smart contract systems like Ethereum, the one thing we know about Ethereum is every 6 months, there will be a programming flaw in a smart contract that causes literally tens of millions of dollars of ether to be lost, sometimes hundreds of millions of dollars of ether. So getting the system reliable and something that will remain reliable into the future is very important. And you don't want to have to be changing the programming language all the time. So the question was, right, how do we design Plutus Core so that it will still be valid 50 years from now? And the answer to that question was we use something 50 years old, System F. So here's the complete definition of Plutus Core. You can see it's not as small as Lambda Calculus, but it's pretty small. That's the complete definition, apart from the constants in the language for doing things like manipulating numbers or strings. And then I mentioned all these different proof systems. One of these is AGDA, and we've just, I wrote a whole textbook on programming language theory in AGDA, and then we used the description of Lambda Calculus in that textbook as the basis for writing out a description of Plutus Core. And going back to this team, one of the people on the team is James Chapman. He's a world leader in how you use AGDA to represent programming languages. So we got him to do all the hard work. So we have this whole thing set up now. Oh, I don't have my napkin. When I came up with this definition, Charles Hoskinson, who runs IOHK, said we ought to call it napkin because it would fit on the napkin. And when we launched Plutus, they printed up napkins. So I've got a napkin somewhere, but it's in a different room, so I won't go and fetch it now. But we've got napkins with this printed on them. Okay, I think that was all I wanted to say about, so we are making use of these ideas in Cardano and Plutus, but not for verification. It would be wonderful to do that. So that was part 2A, I guess, and now we're on to the final part, which is about philosophy. But before I do that again, are there any questions? Okay, shall I move on? You can nod if I should move on.
I'm ready.
Okay, so remember, so normally I don't have much time for philosophy, but you remember, right, Turing's philosophy was actually quite important. This is not nearly as important as what he did with his philosophy. I'm going to do a wee bit of philosophy anyway. So imagine the problem of talking to aliens. So we've actually thought about this, right? This is a plaque that's on the Voyager spacecraft. And it has things on like, well, this is sort of an image of the spacecraft to scale with a couple of people in front of it. Here we've got, they're trying to explain where the solar system is. So this is a schematic diagram of the solar system, not to scale, showing Voyager leaving from Earth and going out this way. And then to explain where the Earth is, they took all these pulsars and they've got lines from each pulsar to where the center of the galaxy. Oh, sorry, one of these pulsars is not pulsar, it's the center of the galaxy. And lines from each of these that are as long as the distance from that pulsar to Sol. And then you can't see it, it's very tiny, but on each of these they've marked a number in binary, which is the frequency of hydrogen at that pulsar. So they've identified the pulsar by the frequency of hydrogen in it. So if we set this to aliens, would they be able to decode this? Well, I think probably understanding that length of a line corresponds to a distance, they could do that. Binary, they could probably do that. What about this bit? I think that depends, right? If they have a visual system like ours, well, right, if Star Trek is right, they'll just look at this and say, wow, they look just like us. Oh, except they don't have pubic hair. But if Star Trek is wrong and aliens are really alien, then this may just be gibberish to them. We don't know. That might be a good thing, right? Because maybe they'll just look at it and say, tasty, let's go eat them up. We don't know what will happen. So an example of the tasty, let's go eat them up is the film Independence Day, where aliens come and destroy lots of big buildings in New York, which back when Independence Day was made was fantasy. And the way they get rid of the aliens is they give them a computer virus. So here's the computer virus that destroys the alien spaceship in Independence Day. And you can see it's written in a dialect of C. It's a dialect that seems to only have opening braces, no closing braces. And how do I know this is C and not Java? It's because the film came out in the mid-1990s, which was, Java still existed then, but that was before Java had taken over the known universe. And at the time I worked at Bell Labs, I thought, wow, that's cool. Something what my colleagues did C has made it onto the screen in a big blockbuster movie. But come on, are you going to be able to program an alien computer in C? I don't think so. If you sent a program written in C to aliens, would they be able to even understand it? I think it's an open question, right? It's just like, will they be able to decode what that is? They might be able to decode the C, they might not. Okay, what if we set them a program in Lambda Calculus? I think Lambda Calculus would be more like, working out the length of a line or working out binary. I'm pretty sure they would be able to work out what the Lambda Calculus meant. So should we call Lambda Calculus a universal programming language? So let's ponder that for a minute. But actually what I want to talk about for a minute is multiverses, right? This has become ubiquitous in popular culture, the idea that there's more than one universe. So this is from a play, and there's only one program note for the play. It says, wherever a horizontal rule appears in the text, it stands for a change of universe. It's a very nice love story. And of course, the characters keep bumping into each other, right? The first time they bump in to each other, the man rejects the woman, and the next time the woman rejects the man, and eventually they get together, and you see all sorts of different variants on this love story. And that's a very common thing to see these days. And right, this goes back down to quantum physics, where the idea is in quantum physics, when a choice is made, maybe that corresponds to two different universes forming, one for each choice. And it's actually used sometimes in science. Like, it turns out that if the small electron constant was a little bit larger or a little bit smaller, that matter would never form. And so the question is, why does it happen to be just right for matter? And people say, well, there are lots of universes. We're in one that has people in it that can look at the universe. So of course we're in one where it's just the right size. There are lots of other ones where it's the wrong size, but we're not in those. That's why it looks to us like it's just the right size. So scientists sometimes use this idea of a multiverse. So, it depends on how good your imagination is, but I can imagine a universe with a different small electron constant or a different gravitational constant. I can't imagine a universe without modus ponens. Just my imagination doesn't extend that far. I don't think it's possible. So this is me being a Platonist again, I guess.
Maybe not.
But I just can't imagine that. So what does this mean? It means any universe you go to, there will be logic. Any universe you go to, there will be Lambda Calculus. We cannot call Lambda Calculus the universal programming language. We can't call it universal because calling it universal is too restrictive.
Omniverse.
So I'll stop there. I'll just finish with one thought. The thing that I hope you take away from this talk is that if you've got a tough job to do, then you should think that this is a job for Lambda Calculus. I'll stop there.
Well, we've got our Lambda superhero here. Is there any other questions?
I have a question. When we're doing proof simplification, we don't actually have the like the Lambda calculus program written down there. So can you perform program evaluation just with the type information?
No, it's about simplifying a proof or simplifying a term. In dependently typed calculi, you end up simplifying types as well because you have bits of program hiding in the type. But generally, simplification is about what you do with terms rather than with types. Did that answer your question?
Well, yeah, it's simplification of the derivation of that a program has a type, I think. You're simplifying the
Yes,
proof.
you can think of it that way, yes.
I have a question. So there's like typical cuts in logic where you have the introduction rule, the principal premise of an elimination rule proved by an introduction rule. There's also commutative cuts where, like when you have like rules that introduce bottom, like if you have falsity, then you can introduce other types of useless work that a typical cut sort of corresponds to. What like program evaluation does eliminating like those commutative cuts correspond to, or is it kind of the same concept?
Ooh, that's a very good question. I should know the answer to that off the top of my head, and I don't. So let's see, does everybody in the class understand about principal cuts? If not, I could go back and just make the point that you were making, right? So in the
Everyone does not
rules
understand it, yeah.
Right, this is a principal cut, right? We've got an introduction immediately followed by an elimination. In the other case was an introduction followed by an elimination. But you could have introductions and eliminations that are far apart. And those commuting rules that you mentioned bring those back together.
Mhm.
So Gensen described how you do that in cut elimination. Provitz described the same thing for acting on terms like this. So there is a
Right.
description of how you do that for terms like this. And basically that corresponds to sort of moving the variables around.
Okay. It's kind of where my intuition took me, but it wasn't obvious to me what it was. So.
Yeah, I would have to, after this call, I will probably sit down and do one of those examples to remind myself of what does that look like in natural deduction and what is the intuitive meaning of that. But
Yeah.
I'm old and decrepit enough that I'm not going to be able to do that on the fly.
Yeah, it's
It's
okay.
a very good question. Thank you for asking it.
I have another question kind of related. So we get this property of, we have the subformula property, and that's what helps you prove that the logic is consistent, correct?
Yes.
Is that the exact same thing? Does it give you exactly the same thing as what they call the cut elimination property? Like, so the
Yes,
cut elimination property, they say then,
essentially the same thing.
okay. So like if a
Cut
logic
elimination
has,
is the proof of the subformula property.
okay, that makes sense.
And you mentioned, as I mentioned before, that the subformula property is useful for proving consistency. But on the programming side, then what that says is you can always simplify to get rid of some intermediate concepts. And so we've done some designs of domain-specific languages, and then we design those so that we know, right, that they introduce certain connectives that you don't need in the final program. So we know they will get simplified away. And so we use the subformula property to prove, to embed a domain-specific language in a more general language, and then to guarantee that simplifying that down will get rid of certain things.
Interesting.
So it has practical application, which is nice.
Yeah, that's very cool. Thank you.
So we wrote a paper on something called quoted domain-specific languages, which explains that idea. Everybody's tired. There are no more questions.
Well, along those lines, Art, do you know of any good applications of interpolation in like translating the logical idea of the interpolant in a proof to does it have any corresponding operation in the programming side?
Ooh, you have to remind me what interpolation
Oh,
is.
it's like that there's a, well, in the sequent calculus anyway, it's kind of either there's a mid-sequent that contains only subterms from the conclusion, and you know, the ones on the left side are negative polarity and the ones on the right side. So there is this kind of like midpoint of a proof is the interpolant in a sequent proof. And I don't know. I mean, well, what's his name? I mean, books have been written on it. What's his? Gabet wrote a whole book on applications of interpolation, but I never really figured out exactly, you know, like what that might correspond to. I've had this kind of idea that maybe now with AI, we might be able to try to use that as an automated proof procedure where you try and guess the interpolant. It's kind of like the middle of the proof. So it'd be like doing binary search for proofs. You kind of like guess the middle and then keep guessing the middle. And anyway, So you haven't really seen any applications of interpolation on the programming side. So I don't know. Maybe
No, I don't think I have.
you know.
But other people might have done that.
Mm-hmm.
So I wouldn't be surprised if you Googled around a bit if you found something.
Yeah.
Oh, speaking of which, I can stop sharing, can't I?
Oh, there we go. That is good.
Have you kept up with the progress in adding dependent types to Haskell at all? And how do you feel about it?
Yes. Haskell's quite a large language at this point, and so retrofitting dependent types to it is quite difficult. I recently, I work at a university, I teach. I teach a course on types and semantics for programming languages. So Benjamin Pierce wrote a really nice textbook for programming language foundations using Coq. I taught from that for 5 years. And I thought, ADDA is much nicer. So, right, in Coq, you need to teach them about proof scripts. In ADDA, you just teach them about propositions as types. And, right, I love propositions as types, and Pierce's book doesn't even barely mentions propositions as types. So I thought my original idea is I'll translate Pierce's book to AGDA. And I quickly realized, no, I don't like Pierce's book. I'm going to write my own book.
I'm with you.
So I wrote my own book. So the book is actually an executable AGDA program. And the first half of it introduces AGDA. And then the second half uses AGDA to do formal models of Lambda Calculus. And I think AGDA is what Haskell wants to be when it grows up. So my answer to the question is I'm not going to wait for Haskell to get dependent types. I'm just going to shift over to using AGDA.
So, but what about Edwin's, Brady's, Idris?
Idris is nice too. The difference in emphasis is AGDA was designed for people who want to do proofs.
Uh-huh.
Idris was designed for people who want to write programs.
Uh-huh.
And I quite like doing proofs.
Uh-huh.
So I'm going with AGDA, but Idris is nice too.
The work translating AGDA to Haskell too is kind of interesting to me. I don't know exactly how it works, but there's like the AGDA 2HS
Yes.
package that can do that. And I don't know how that works, but that's interesting.
All right. Well, Philip, thank you so much. If there's no more questions.
Well, thank you for inviting me. Thank you to everybody for your attention and for all the good questions you asked.
Any more takers? No. Okay, well, let's give him a hand, even though it's hard to hear if you're muted. Thank you so much.
Okay.
Yep.
Thank you very much, everybody. And thank you for bearing with me for the technical problems at the beginning.
No problem. All right.
Thank you.
Bye.
Thank you.
Bye.